Okay. Now, we consider the case of n even. If n is even, like suppose n is equal to say 6. So, I have got H 0, H 1, H 2, H 3, H 4, H 5. So, total 6. So, I will divide it into just 2 halves. N is 6, the capital N. One is on this side, another on this side, and I will put a mirror here, and I will impose this condition H 2 equal to H 3, H 1 equal to H 4, H 0 equal to H 5, like that. So, one half will be n by 2, another half will be n by 2. Okay. So, n by 2 is 6, n is 6, n by 2 is 3. So, there will be 3 terms here, which is go from 0, 1 up to 2. All right. So, in general, I will have H 0, H 1 dot 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 total n by 2 term. So, it will go up to n by 2 minus 1. So, then 0 1 up to n by 2 minus 1 means total n by 2. Then a mirror here, and then next is n by 2 dot 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 and I will have this mirror image symmetry. These two will be same, these two will be same, these two will be same. In general, H R and H, okay, because H 0 same as H n minus 1 minus 0, H 1 same as H n minus 1 minus 1, that is n minus 2, H R same as H n minus 1 minus R. Okay. So, that means H R will be, this is my condition in short, starting from R equal to 0, 1 dot dot dot, all right. Now, if I take again DTFT, and they are same. So, there is no independent guy at the center, unlike the previous case, because the total number was odd. So, there was an odd man out in the middle, we had to handle it separately. Here there is no such case. I have exact division into 2 sides, n by 2 on this side, n by 2 on this side, and we have got a mirror image symmetry. So, for the DTFT, H r and H n minus r, H n minus 1 minus r, I will take them to be under one bracket, and H n minus 1 minus r will be simply replaced by H r. So, 2 terms will be combined together with the coefficient H r, and that is r for 0, r for 1, r for all. That means, DTFT will be r starting from 0 up to n by 2 minus 1, typical rth case H r, and again H r, but this H r is with respect will have e to the power minus j omega r. This H r, that is H n minus 1 minus r, which is same as H r under this condition, that will have e to the power minus j omega into this index. And as before, I take out e to the power minus j omega n minus 1 by 2. Okay. Then what will happen? It is very much like the previous case. H r, I have to bring it back inside. So, it will be with a positive sign, j omega n minus 1 by 2 minus r, and where minus j omega, already n minus 1 was present. After that, n minus 1 by 2 has gone. So, we will be left with another n minus 1 by 2 by r, as we did last time, and this is twice cos this. So, twice I put this something in summation r equal to 0, H r cosine omega into this phase part. Once again, phase is linear, phase is this with a negative sign, this is causal, that is where it is coming. Okay. But here this is a constant. So, it is a linear phase, and as before, this is the magnitude part. I am assuming that we are designing the coefficient such that at least within the band omega c to plus omega c signal band. This does not change its sign, does not become negative, it remains positive. So, because if it changes its sign, if it becomes negative, then immediately it will mean a shift, phase shift by e to the power j pi, and the mod of this quantity will come here, and there will be e to the power j pi coming, which means to this phase another pi will get added. So, it will be like, I mean, phase was falling down and suddenly it will go up by pi and it will start falling down. So, it will not be perfectly linear. So, we are assuming that we are designing the coefficient such that within this band it does not change its sign, does not become negative, and also magnitude wise also it does not, it oscillates, but does not change much. So, it is kind of constant. Only thing is capital N is even now. So, n minus 1 by 2 is a fraction. Okay. That is why this will not be physically meaningful, this delay. That is why we prefer n equal to odd case, that will amount to a perfect delay of the signal. Okay. So, this is possible only when the filter is FIR. All right. Now, for this FIR, for this linear phase systems, some properties are important. Suppose I, instead of discrete time Fourier transform, I take the Z transform. So, n equal to odd case Z transform. So, I go back to that n equal to odd case. Okay. So, instead of e to the power minus j omega, it will be z to the power minus 1, e to the power minus j omega, it will be z to the power minus r. So, here a z will be this guy separately, but e to the power minus j omega into this, instead it will be z to the power minus this. Okay. Normally, z is replaced by e to the power j omega in dtft. If you want to go the other way, e to the power j omega wherever you find, that is z. So, z to the power minus this, z to the power minus this. There is a way to get back the z transform. You can, okay. And this summation h r, this will be z to the power minus r, and this will be z to the power minus n minus 1 minus r. Okay. Now, as before, I will take out, sorry, this is not z to the power, sorry, this is not z to the power minus 1, this is z to the power minus this part. N minus 1 by 2. So, from here also I take out this z to the power minus. So, this remains as it is. I have taken this out, and from here also I take out. Then what happens? This has gone out, so I have to cancel it. So, this will become z to the power plus n minus 1 by 2 here. So, it will be z to the power n minus 1 by 2 minus r, and here z to the power minus, already n minus 1 was present, out of which n minus 1 by 2 has gone. So, another n minus 1 by 2 will be present, and r. This is the situation. Now, what is this z transform? H z as such is H 0. Before I wrote in this form, a general H z is of this form, right? H 1 z inverse, H 2 z inverse 2, dot 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 say H, right. Now, z inverse, if you take it to be some variable, complex variable, say q. So, So, it is h 0 plus h 1 q plus h 2 q square plus dot 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 plus h n minus 1 q to the power n minus 1. So, it is a polynomial in q is the power sub q up to degree or up to degree is n minus 1. So, you can factorize it, there will be all first order factors. So, first order factors will be of this form, some constant you can take out, maybe a, then to 1 minus maybe some root a 0 q, q is Z inverse, right. Then 1 minus a 1 Z inverse. After all, to make life simple, you can replace all Z inverse by q. So, it will be q, q square, q cube up to q to the power n minus 1. So, it is a polynomial in q up to the degree q to the power n minus 1. So, this polynomial can always be factorized into first order factors. The factors are in this form. Okay, I am forcibly keeping a 1 here. So, that when you multiply the factors of 1 comes, that 1 times a, which will be giving this term h 0. So, 1 minus a 0 Z inverse, 1 minus a 1 Z inverse, like that dot 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 up to 1 minus a, how many terms? Zero 1 n minus 1. So, n terms. Okay, so it should be n minus 2, because 0 1 up to n minus 2, that means total capital N minus 1. So, Z inverse, Z inverse, Z inverse, we multiply up to capital N minus times, then only leading power gets this. So, it is just that. Okay. So, you can factorize like this. Now, if you, what are these factors? That a 0 is a root, that is, if you take z equal to a 0 into a 0 inverse, that is 1, 1 minus 1 0. So, h z becomes 0. That is why h z has a 0 at z equal to a 0, h z has a 0 at z equal to a 1, h z has a 0 at z equal to a n minus 2 dot dot dot, right. This is a general situation. Now, in this case, for this filter, this is my z transform h z, I am writing like this. Suppose it has a 0, suppose h z, this special h z, not this general case, h z has a 0 at suppose z equal to say a. That means, if I put a here and a here, obviously, this factor will become 0, this cannot be 0. Okay. We are not considering a equal to infinity, because if a 0 is not 0, this filter, this general z transform, even if you put z equal to infinity, this parts go to 0, but h 0 remains. Okay. So, that is the reason we cannot have z equal to infinity here, as this factor will become 0 at z equal to infinity, but overall thing will not be 0, because after all this is nothing but this, and here if you put z equal to infinity, this part goes to 0, but this remains. Okay. Therefore, if I have a 0, if this whole thing has a 0 at z equal to a, that means this inner part will become 0 at z equal to a. Okay, that is a to the power plus a to the power minus minus r, this equal to 0. Then my claim is claim h z also has a 0 at z equal to 1 by a, because if you put 1 by a here inside, what will happen? 1 by a means a to the power minus this, and 1 by a z equal to 1 by a means a to the power plus this. Okay, I do not have to write it. Suppose instead of a, we have put a here, a to the power this part, if you call it n minus 1 by 2 minus r, if you call it L. So, z to the power L plus z to the power minus L, minus the same thing L. That means a to the power L and a to the power minus L. Okay. This is becoming 0. This summation here is becoming 0. If I now replace z by 1 by a, this will become 1 by a whole to the power this, that is 1 by a whole to the power L means a to the power minus L. So, a to the power minus L will come, and if z is 1 by a, so to the power minus and then minus 1 by a whole to the power minus this. So, 1 by a means a to the power minus 1 whole to the power minus this. So, minus minus plus a to the power plus this will come. Okay. So, this will go here, this will go here, and summation remains same, so it will become 0. Okay. So, this proves the claim that if it has a 0 at z equal to a, then it has a 0 at z equal to 1 by a. Okay. So, they are reciprocal pair. Zeros of a linear phase system are a reciprocal pair. Alternatively, if I have got two factors, one having 0 at a, so I have got one factor. So, z equal to a means a into a inverse, that is 1, 1 minus 1, 0. Another is at 1 by a times z inverse. Okay. So, if I construct a system, second order system by multiplying these two factors only, one having root at a, 0 at a, one having at 1 by a. So, it is just a small system, second order system or other subsystem by taking out two factors out of them, one at 1 a, one having root at a, another having root at 1 by a. If I multiply these two, you will have 1 minus a plus 1 by a into z inverse, and then a into 1 by a. So, that is 1 minus minus plus. So, z inverse 2. So, if this is the transfer function of a subsystem, corresponding impulse response will be 1 from here, then minus a plus 1 by a, the next coefficient is 1. And you see it satisfies that mirror image symmetry. It is a filter now of length 3, H 0, H 1, H 2, and this is the where mirror will be present. So, this is the odd man guy. So, let it be what it is. On this side I have got 1, on this side I have got 1. So, phase of this will be linear. So, we can take out one subsystem out of it, phase will be linear. Okay. That is, as the roots occur in reciprocal pair, you can take out those two roots, those two factors, and make a subsystem just of this transform of this product of this. So, it is a second order filter. This will again be a linear phase filter, because its impulse response is what? H 0, this is H 1 into z inverse, and this is H 2 into z inverse. H 2 is 1, H 1 is minus a plus 1 by a, H 0 is 1. And you see this filter impulse response, total length is 3. So, odd. So, there is an odd man out at the mirror position, and I need mirror image symmetry. So, if you go to left hand side by you have 1, if you go to the right hand side you have 1. Okay. One more thing, when you factorize, this is again the general transfer function FIR. When you factorize, it is not guaranteed that all the coefficients will be real, okay, because if you have a 1 plus x square, you can factorize into first order factors, but these roots will be complex. But if the original H 0, H 1, H 2 up to H n minus 1, if they are real, H 0 real, H 1 real, H 2 real up to H n minus real, then my claim is if there is one root which is complex, then there must be another root which is a conjugate of it. That is, if there is a root, suppose H 0, H 1 dot H n minus 1, they are all real. Then H z is H 0 plus H 1 z inverse plus okay. They are all real. Now, if z equal to a is a root and a is complex, then there must be another root at z equal to a star, the conjugate of a, and then you will have the product a z inverse, another is a star z inverse. Together if you multiply just these two, what will happen is 1 minus a plus a star z inverse and a into a star, that is mod a square z inverse 2. And you see a plus a star is real and mod a square is real. So, you get a polynomial with real coefficients. So, this way whenever you have got a complex root, there will be another root conjugate of it. You can take the two factors, product will be a second order term, will be a second order polynomial with all real coefficients. And there will be many such second order polynomials where all real coefficients, whole product is H z, and H z will have real coefficients. Okay. But if I do not have a star with a, then there is problem. That is why whenever there is a complex root, its conjugate will be there. Now, suppose I have got a linear phase system and with real coefficients. Suppose I have got a linear phase system with real coefficients. So, I know if it has a root at a, from linear phase property, it will have a root at 1 by a. But since coefficients are real, if a is complex, that is, it is given H z linear phase. Means if z equal to a is a root, is a 0, then z equal to 1 by a also a 0. But given that H 0, H 1 dot 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 H n minus 1, they are all real. Okay. In that case, if a is complex, we have seen a star also must be, if a is a root, a is 0, earlier have seen 1 by a is 0, but again under this condition that the coefficients are real, then if a is complex, then a star must be a root also, must be a 0 also. But since the filter is linear phase, this also implies 1 by a star also is a 0. Okay. First, for any root a, any 0 a, 1 by that is a 0. Okay. And separately, if the filter coefficients are real, if a is complex, a star is a 0, and therefore 1 by a star also 0, because filter is linear phase. So, together we have got a star, 1 by a, 1 by a star, 4 roots together. It is called conjugate reciprocal pair, a and its reciprocal 1 by a conjugate a star and its reciprocal 1 by a star. So, these 4, I mean in these cases under for a linear phase system, if there is a root, complex root, then there will be 4 such roots together, it is a quadruplet. If a is complex, a star must be present, because filter coefficients are real, and since they are linear phase, both 1 by a and 1 by a star must be present, which means in the complex plane it will look like this. If there is one root here, say a, this is a suppose is r into to the power j theta, then how about a 1 by a, 1 by r into to the power minus j theta. So, here r is the phase, r is the magnitude, so much is r, so much is theta, right, so much is r and this angle is theta. Now, r is greater than 1 means 1 by r will be less than 1, and angle is now minus theta in this direction. So, here will be one root, this is minus theta, this is your 1 by a, and on the other hand a star is another root which will have same magnitude, only phase is opposite. So, angle will be minus theta, but same radius r. So, here is one root, here is one, same radius r. So, but angle minus theta. So, this will continue, it will come here, this is a star, okay, and 1 by a star, another root, that will be 1 by r e to the power j theta. So, angle is again plus theta, but magnitude is 1 by r, which is less than 1. So, this much. Okay, these are the 4 roots and they form a quadruplet. Okay. So, this is conjugate of this is conjugate of this is reciprocal of this is reciprocal of this. If you take out these 4 factors now, 1 minus a z inverse, 1 minus 1 by a z inverse, and then 1 minus a star z inverse, 1 minus 1 by a star z inverse, you will see it is a linear phase system. Okay. Obviously, if you multiply them, coefficients will be real, because if there is one root at a, there is one root at a star. So, if you multiply them, you will have a second order polynomial with real coefficients. If you got 1 by a, 1 by a star. So, 1 by a's conjugate is 1 by a star. So, if you multiply these two, you will have a second order polynomial with real coefficients, and then multiply the two real second order polynomials with real coefficients, you get a fourth order polynomial with real coefficients. So, the product will be guaranteed to have real coefficients, that is done. But now, phase wise, if I take up these two together, it is again we have seen earlier, and it is just z inverse 2, and it is this is one subsystem, this is one subsystem, and they are cascade of the two. What is the impulse response here? 1 minus and 1, and here 1 minus a star plus 1 by a star 1. The second order, so total term is 3. Okay, length n, length is odd. So, there is a mirror here, this is odd man out, and from the mirror if you go to the left, you get 1, to the right 1. So, it is symmetry. So, this will be linear phase, this will be linear phase by the same way. So, in terms of in the DTFT domain, this might give rise to some 1 h 1 e to the power j omega, which will have magnitude part into phase will be some constant k 1 omega, and this will be giving rise to 1 h 2 e to the power j omega, which will have a magnitude part this phase some k 2 omega. If you multiply the two, because they are cascaded, phase, this magnitude will be product of the two, and phase will be added. Okay, so, phase will be continued to be linear phase. So, it means if I have a very large order linear phase FIR filter with real coefficients, I can factorize the transfer function into first order factors, and then take out these quadruplets and form subsystems, which will be themselves in linear phase. Now, suppose this A is having magnitude 1. In that case, what will happen? Suppose A is in having magnitude 1 here. So, A is just e to the power j theta, but this is theta. Okay. Then A 1 by A is e to the power minus j theta, which is same as A star, and 1 by A star is e to the power j theta. So, this is again this. So, A is same as 1 by A star, 1 by A is same as A star. So, in this case you see is enough if you have just first if you multiply with 2, since 1 by A is A star, 1 minus A z inverse, 1 minus A star z inverse. So, product will be a second order polynomial with real coefficients, because it is A star, 1 by A star. And earlier we have seen that if you have A and 1 by A, then the resulting filter will be linear phase. So, you can here take out just 2. Okay. In fact, you take out just these 2. In fact, there will be 2 poles only, because whatever is conjugate, that is also reciprocal. So, there is no 4 points. If this is one pole, it is reciprocal as well as conjugate will be this and vice versa. So, you will have just two roots, not poles, 2 zeros, okay, not 4 when they are lying on the unit circle. And if you take the 2, make a cascade, it will be having both linear phase property, and also since 1 by is A star, it will give rise to a filter of transfer function that has all real coefficients. Some more special case, couple of special cases. Suppose you are here, okay, that is A is just 1. In this case, A is 1 means A 1 by A, that is 1, they are same, A star because A is real, and 1 by A star, they are all same. So, we will have only one term, 1 minus A e to the power or A Z inverse, right. Now, this is first order, but this has a real coefficient. So, that part is satisfied, but is it linear phase? Answer is no, because it is a length 2 filter 1 and minus A, and 1 is not same as minus A. Okay, length 2 even. So, this should have been same, they are not same. Therefore, in this case if A is here, then there must be, you see, there will be one more term, that is this 1 minus A Z inverse should repeat, because then what happens, you will have A is 1. So, you will have 1, I mean A is 1, right, this is equal to 1, this is equal to 1. So, 1 minus Z inverse, 1 minus Z inverse, 1 minus 2 Z inverse 2, sorry 1 minus 2 Z inverse 1 plus Z inverse 2. So, this filter now is having again real coefficients and impulse response 1 minus 2 1. So, length 3, there is a mirror here, this minus 2 is an independent guy, to the left you have 1, to the right you have 1, then it is linear phase. So, in this case if the 0 is here, you cannot have just this 1 minus A Z inverse term alone, there must be 1 minus 1 by A Z inverse. So, that the product is linear phase. On the other hand, if you have here, then A is minus 1. Okay. See, earlier what we had 1 minus A Z inverse, A is 1, so 1 minus Z inverse. So, your filter was 1 and minus 1. So, they are not same, length 2, but they are not same. But in this case, you will have 1 plus Z inverse, because A is minus 1. So, this amounts to a length 2 filter with impulse response this 1 and 1 from here 1 1, right. So, 1 1, and this is symmetric, length 2. So, there is a mirror in between length. So, in this case you can have only one factor like this. Okay. So, that is all for the linear phase systems. Thank you very much.